Howdy, this is Jim Rutt, and this is The Jim Rutt Show. Today's guest is Lee Smolin, a physicist who is on the faculty of the Perimeter Institute for Theoretical Physics in Waterloo, Ontario. Lee, could you tell us a little bit about the Perimeter Institute?
Yes, Jim, and thank you very much for inviting me. The Perimeter Institute is a public-private partnership that was started by Mike Lazaridis, who was one of the founders, or the founder of Research in Motion. He was the inventor of the smartphone and the BlackBerry, if you remember the BlackBerry.
Indeed.
He got this idea around 2000 that he would like to do something for science. And he indeed was a big fan of theoretical physics. And he found himself all of a sudden, because it happened very quickly, with the wealth and the freedom to do something dramatic for the science of theoretical physics that he was such a fan of. And indeed, he wanted to be a scientist when he was growing up as a poor immigrant to Canada. And so he discussed it with a number of people. And one of them was a very extraordinarily resourceful, just an extraordinary person. I don't know how to characterize him in small bits. Howard Burton, who was just getting his PhD then from the University of Waterloo in quantum gravity, which is my field. And Howard had no administrative experience whatsoever, no experience in the academy as anything other than a student or a graduate student. But Mike saw something in him, which was a great vision and a great leadership, and picked Howard first to do research about the shape of the new institute they were talking about, and then to actually be the first director.
That's an amazing story.
That is an amazing story, and it's a lot to do with our success.
Is he still there as the director?
No, he was the director until 2006, and then he left and now lives in the south of France, where he has an interesting life, and he also, I think, is making podcasts.
Well, life is good in the south of France.
Life is good in the south of France, and he's there with his family. Our second director was Neil Turek, who just ended his 2 terms of 10 years. And Howard put us on the map and gave us a set of principles and structure, which made us quite distinctive and different than all the other centers for theoretical physics in the world. And Neil then took that and grew us by a factor of 3 into a formidable center for research.
I'm really glad that the BlackBerry guy did that. I mean, that's frankly a much better use of money than yet another 200-foot yacht, I would say, right?
Yes. No, Mike is a person with vision, a person with enormous generosity, and his initial contribution was $100 million, which was made as a kind of challenge to the governments of Canada and Ontario to match, and that offer of match has been made twice more and match. So his funding has been critical, but also has been funding from the province of Ontario and the government of Canada. So we have strong support from the public, from the governments, and from the private sector, and that gives us a formidable strength. It gives us freedom.
Indeed. And, I've been associated with the Santa Fe Institute for the last 17 years, and it has a different trajectory, but a similar story in that it's an independent, standalone institute founded by a small group of visionaries and has gone on to do some pretty interesting things, though not at the scale in terms of at least headcount of the Perimeter Institute. Anyway, the reason I asked Lee to be on our show today was that I recently read one of his books. I've actually read several of his books, but just recently I read Einstein's Unfinished Revolution, The Search for What Lies Beyond the Quantum. It examines what's often called quantum foundations, which examines the question on what's really happening beyond what our calculations tell us in the world of the tiny, where quantum mechanics reigns. This is an area I've been interested in for a long time. The first thing I read on quantum foundations was a popular book by Nick Herbert called Quantum Reality, which I probably read 30 years ago. And it's one I recommend. I don't know if it's still very accurate, but it was certainly evocative and has gotten me thinking. I've been sort of following the area outside of the right corner of my eye ever since. So we're going to talk about quantum foundations, but before we do that, Lee, could you start with a description of quantum mechanics that's suitable for an intelligent but not necessarily scientifically trained audience?
That's the audience I always try to speak to, Jim. Quantum mechanics is the science of the atomic world, of radiation, atoms, nuclei, molecules, and so forth. It was invented in the early part of the 20th century and is still, I would claim, not yet in finished form. Quantum mechanics is unusual as a physical theory in that it seems to require that we give up some of the intuitive or seemingly obvious assumptions about nature and our perception of it, mainly that what's true about the natural world is independent of our beliefs or our knowledge of it. And this notion that challenges the very idea of realism, that science is about the real world as it really is, independent of our dreaming about it, imagining it, or knowledge of it, is the key issue on which the debates over the last 70, 80 years have turned and continue to turn.
Very interesting. Now, one key question before we get into foundations that I know befuddles the layman and may even befuddle some of the scientists studying the area is, to what degree does quantum mechanics introduce true randomness into our world? You know, the thought experiment I've used to try to think about this is, suppose we had 1,000 boxes with a measured radioactive source that had a mean decay rate of 1 hour. We had a Geiger counter in each box, and each box was associated with one of the top 1,000 cities and population in the world. And the first 100 to decay dispatched an ICBM with a nuclear warhead to detonate over that city. Kind of a grisly example. But is that process of what 100 cities get destroyed truly random, whatever that really means?
Truly random means has no underlying cause. And according to quantum mechanics, as was formulated in the 1920s, it is indeed true randomness. There is no cause of when there's a decay rate for a radioactive atom, which is the half-life, the amount of time it will take half of a population of them to decay. But which decays when and what order is, according to the principles of quantum mechanics, entirely random. Now, whether that's really true, whether there's a hidden underlying cause that's just not described, so we have an incomplete description of reality, is another way to put the battleground that people fight over. Einstein, right off the bat, and a number of the other founders of quantum mechanics like Erwin Schrödinger and Louis de Broglie, argued that quantum mechanics was incomplete, and that there was hidden information, or as they came to be called, hidden variables that if we knew them would allow us to predict exactly which atom would decay when. And the claim then is that quantum mechanics is a kind of handy approximation to the truth, but doesn't contain the whole truth.
Great. So that's a great transition to the question of quantum foundations, right?
Quantum foundations is the branch of physics where we focus on these fundamental questions about the nature of reality and randomness and so forth as relevant for the quantum domain.
Yeah, could you give us a brief review of what some of those questions are and maybe some of the specific leading interpretations, and why is there such disagreement about what quantum mechanics means? I mean, naively as a layman, one thinks of science as the world of things nailed down mostly. But, these discussions of quantum foundations range very, very widely, as you know better than almost anybody. So if you could address what some of these interpretations are and why there's so much disagreement still.
Well, I think there's disagreement because the options are limited and the issues are quite profound, and it's the kind of thing that we're deeply interested in. Those of us who go into science seriously, whether a layperson like yourself or those of us who get trained as a professional scientist, have this interest because we care about the nature of reality. We want to tell a story to our children and our grandchildren about what the world is and ultimately how we fit into it. And the fundamental laws of physics, the fundamental laws that shape the forces that guide the elementary particles that are the cause of atoms and molecules and everything that we're made of and so forth, is of fundamental importance now. The way that quantum mechanics was originally formulated in the early part of the 20th century, it was instigated by Einstein and a few others, but put into final form in the 1920s by a number of people. Niels Bohr, Werner Heisenberg are two of the most prominent, Wolfgang Pauli, Paul Dirac, an Englishman. There were maybe half a dozen. And these people were philosophically not inclined to realism for reasons of their own, which is interesting to explore. So they presented a theory in which randomness was fundamental, in which there was no determinism, and I can explain exactly what it means, why it lacks the idea that things are determined, as the future is determined from the past and the present. And in the version of quantum mechanics that they proposed, the state of a system does depend on what you choose to measure. And what's true about a system does depend to some extent on what questions you ask about the system. So there was a kind of unification, the way they saw it, a unity, not in the usual sense of unifying the different forces, but a unity of reality in the observer. They saw the reality as something that is created by the observer as the observer finds out about it. He also influences and constructs reality. And this was very pleasing to those of that generation. They thought that they saw it as an irrefutable and irreversible change and revolutionary change in the idea of what science is and how we relate to nature. And it was repellent to those who had the older view that the world is independent of our talking and thinking about it. Okay, so this was an anathema to those who had the older, more traditional notion of reality as independent of our knowledge. And those included Einstein, Schrödinger, de Broglie, and a bunch of others. And so there are two groups which take a widely different view. And what they prescribe is different. Basically, when you come to think about these questions, you face a question. There's a kind of branch in the road at the beginning of your thinking. Do you think that quantum mechanics is correct? And the problem is just how we think and talk about it. But that the basic equations, the basic predictions of quantum mechanics are correct and complete. And if you do, then you're interested in just having the most elegant and useful language to describe this strange new reality. And then you're interested in what's called the interpretation of quantum mechanics. And as you hinted, there are lots of different interpretations, and I can outline some of them. But that's only half the subject. If, on the other hand, you think that quantum mechanics lacks the full picture, that it's incomplete, then you're looking for new knowledge about nature to complete it. New hypotheses, maybe new particles or new degrees of freedom, new forces. And then you're functioning not like a philosopher looking for a different interpretation, the most elegant way to say things, but looking for a different physical theory. And that's the work that I do. I've certainly aligned myself with that branch of the subject, and that was the part of the subject that was started by Einstein and de Broglie and Schrödinger.
Question back to the interpretations. Probably the dominant interpretation since the founding of the field, at least since it coalesced, is the so-called Copenhagen interpretation. Could you tell our audience about what that is? And I realize it's not your interpretation, but at least provide that background for people so that they know what the majority of the field has thought for the majority of the time.
Yes, although I should say there are very few pure Copenhagenists left alive at this point. But they were the first. They were called the Copenhagen interpretation because Niels Bohr, who was the first person who successfully applied the ideas about quantum physics to the atom and developed these ideas of energy levels and orbitals and so forth. So he was a very important scientist for the development of the theory. And the Dutch government, in conjunction with a beer company, Carlsberg Beer, basically set him up in an institute with secure funding and beautiful building and a beautiful house where the director lived and could entertain visitors. And this center, what became called the Niels Bohr Institute, became the creative center for the birth of quantum mechanics. All of the young people who played a key role, like Werner Heisenberg, Wolfgang Pauli, and so forth, were frequent visitors to the center or were students or postdocs there. And so that's why the ideas that they came up with are called the Copenhagen interpretation. Now, to illustrate how they talk, and let me emphasize, this is a more radical point of view than most people now think you have to go to make sense of quantum mechanics. But it's very evocative, and it's a good place to start. Niels Bohr, for example, talked about the question of whether an electron is a wave or a particle. Einstein had shaken the world up, and this was the first intimations of quantum physics in about 1905 when he talked about light being both a wave and a particle and seeming to have aspects of both natures. And that's almost paradoxical because a wave is something which is spread out and flows through all the available space open to it, whereas a particle is always on a trajectory and is always somewhere and is always going somewhere. So waves and particles are quite different. What Bohr said is that an electron or a photon is neither a wave nor a particle. These are human-invented conceptions that we impose on not the particle, but the whole experiment we set up designed to reveal the nature of the particle. And there are some experiments which are naturally designed to bring out the wave properties of a photon. There are other experiments which are designed to bring out the particle properties. So we use these languages. We choose which language is most appropriate for the whole experimental situation. And we demand only one thing, a kind of consistency, which is that there's no experiment that will lead us to try to use the wave picture and the particle picture at the same time, and therefore risk contradicting ourselves. And this style of thought that the world could be fully described only by properties which contradict each other if they were forced to be used at the same time, but are sometimes used one, sometimes used another, was what Niels Bohr called complementarity. And he thought that he had made a great philosophical discovery. In fact, he thought he had gotten it from the Bible, from the mystic writings of the Kabbalah and other religions. He talked about the complementarity between God's love and God's justice, for example. God, we teach, loves each one of us, but God also has justice, which is strict, according to the religious teachings. And how can God love us and be a strict disciplinarian is a mystery. And it's a mystery, not just for God, but I'd say as a parent, it's a mystery.
One thing us laymen often hear about the Copenhagen interpretation is the very shorthand saying, shut up and calculate.
That's not really part of the Copenhagen interpretation. What happened, the shut up and calculate, is from another generation of scientists. You see, what happened is that the generations that made quantum mechanics, like Bohr and Heisenberg and Einstein and de Broglie and Schrödinger and all these people, were scientists of a certain type. They were deep thinkers, and they were very philosophically oriented. They were influenced by philosophy. They knew the history of philosophy. They would often be talking about what their favorite philosophers, whether it was Leibniz or Kant or Husserl, would think of these developments. And they were therefore they oriented what they were doing in the history of thought, in the history of philosophy. Then there came a later generation, people who were 10, 15 years younger, who just began their studies when quantum mechanics was invented. And they weren't interested in these philosophical discussions. They thought these philosophical discussions were a waste of time. And there was instead so many opportunities to use the new quantum mechanics to break open an understanding of chemistry or nuclear physics or solid state physics or astrophysics. Everything from how a superconductor works to how a star burns energy was open season. And it was an extraordinary period, this sort of from the 1930s into the 1970s. And during that period, pragmatism was espoused and was emphasized. And people who would have been more fitting of the earlier period, who came into science asking philosophical questions, were told that was no longer relevant and to shut up and calculate.
Well, thank you for that distinction. That's a historical distinction I was not aware of.
Can I give an example? Freeman Dyson is somebody you may have heard of and read. Indeed, he's a brilliant scientist and a brilliant writer. And there's no shortage of good things I could say about Freeman. I've also been blessed to have met him. I can almost quote him from memory. Freeman said about this, that usually it's the young people who are revolutionaries and the older people who are reactionaries. But his generation came into science taught by an older generation who were all revolutionaries and who were all still engaged in these philosophical arguments left over from the revolution they had made. And so he and his generation had to be different, and they had no choice but to be reactionaries and to be pragmatic rather than philosophical.
Well, it's interesting. Those of us who are parents sometimes see that pattern in our children, right? That they react against some of our structures and define themselves in an alternative way. So it's something that certainly makes sense kind of from a human psychology perspective. Let's get back to your arguments. In the book, you argue for the realist branch, and you go into some of the history of that. Could you, lay out where the realist branch came from and who some of the leading people are? And, where you see the realist branch today?
The original realist was, of course, Einstein. And Einstein objected very early on to the philosophical tone of the writing of first Niels Bohr and then the younger generation. Niels Bohr was kind of halfway between Einstein and the generation of Heisenberg, just to paint the picture. Heisenberg and his friends and colleagues were sort of born as of the turn of the century. So they just missed being drafted into the First World War and were in their early 20s while quantum mechanics was being developed in the late 20s. And only really one of those, of that generation, was a realist, and his name was Louis de Broglie. And he was very important, universally admired, because he had taken the idea of the wave-particle duality of light that Einstein had put forward and said also an electron could be sometimes a wave and sometimes a particle, with the same kind of mysteries attendant. And indeed, anything, all matter, would have both wave and particle properties. And de Broglie drew from those ideas some predictions, including the idea that you could diffract electrons in a crystal the same way you can diffract light. And this phenomenon of electron diffraction was seen by some Americans at Bell Labs in the early mid-1920s, and that solidified de Broglie's reputation and fame. And indeed, he, not too long after, won the Nobel Prize for that crucial innovation. But de Broglie went on to say, what's the resolution of the puzzle? How do you, from a realist point of view, avoid the idea of complementarity and observer dependence and observer intervention? He said, well, let's suppose that there are both waves and particles. And there's always a wave, and it flows through the experiment, taking all the available paths. And there's always a particle which follows the wave. The wave is known as a guidance wave, and it guides the particle. And so this double theory in which there are both waves and particles, de Broglie developed and proposed. He called it the pilot wave theory because the wave was a pilot or a guide to the particle. And it gave predictions and explanations which were equivalent to, in many cases, in a few cases, better than those given by the quantum mechanics that his colleagues had developed. So there was, from the very beginning of the subject, a realist alternative, this pilot wave theory. Einstein, it turned out, had also come upon that idea and had written down a pilot wave theory for photons, which he, however, found some problems with and got discouraged. And although he wrote a paper about it, he withdrew it from publication and he never presented it and never much talked about it. But Einstein had also considered that alternative. So it's a kind of a mystery. For example, in 1927, there was the first conference, which was held in Brussels, called the Solvay Conference, where all the important people in quantum mechanics got together for the first time and gave talks to each other about the new physics. And de Broglie was there, and Einstein was there, and de Broglie presented his pilot wave theory. So there was no excuse not to know about it. All the founders must have been aware of it, but it was never taken up. It was never taught. It was never made part of the theory that was described in textbooks. It was as if he didn't exist in a certain sense.
Why was that, do you think? Well, how do you think that his pilot wave theory was almost erased from history?
It's a very interesting question. It's a question about the history of science and the sociology and psychology of scientists, which are not fields that I'm expert in. But let me mention one part of it. A very important mathematician of that day was somebody called John von Neumann, a Hungarian of that same generation. And indeed, von Neumann did many important things. One of them was he invented the standard computer architecture in the 1940s that all the computers use now, with memory separated from processing, for example, was his innovation. But he was a very important mathematician all over the field of mathematics and science and engineering. So, which is to say, he was a very admired and influential guy. And in 1933, I believe, he published a book called The Mathematical Principles of Quantum Mechanics, in which he gave a mathematical proof that there could be no alternative, that a theory that was more complete, that filled in the missing information than quantum mechanics, would have to be self-contradictory or disagree with the experiment. And this theorem, this impossibility proof, as it was called, was very influential. And for the next 20-something years, whenever anybody would talk about why can't there be a more complete description, somebody would say, but you're naive, you haven't studied everything. You have to study von Neumann's proof. Von Neumann has proved it's impossible. And now this is what's really bizarre, is that de Broglie's pilot wave theory was a counterexample to this claim. And by its very existence, de Broglie's pilot wave theory showed that von Neumann's theorem must have been incorrect. Even de Broglie fell for it. Even de Broglie, after the 1930s, who told people who came to him and said, what about your pilot wave theory? And he said, well, von Neumann has proved that's impossible. Now, here's the really, really interesting part of the story. There was a mistake in von Neumann's proof. Great mathematician as he was, he made mistakes, and there was a mistake in that proof. And there was a mathematics student called Greta Hermann who was doing a PhD in the 1930s and was a friend of Heisenberg and some of these other people. She was also a PhD student of Emmy Noether, who was a very important mathematician for some work having to do with the role of symmetry in physics. So which is to say that Greta Hermann was a person who was well situated and in the center of things. And she took to heart the message to study von Neumann's theorem, and she studied it, and she found there was a big mistake at the center of it. Roughly speaking, he assumed what he was trying to prove, which is a way even very talented people can mess up sometimes. So he was a great mathematician, but his proof was erroneous. And the proof that his proof was erroneous was seen and worked out by Greta Hermann and published in about 1935. It should have been obvious to anybody anyway by the existence of de Broglie's pilot wave theory. There is an alternative history in which people read Greta Hermann and credited her and began to work again on the pilot wave theory in the middle of 1930s. But that's not what happened. What happened is that it took another physicist, this one an American called David Bohm, to reinvent the theory, that is de Broglie's pilot wave theory, which he did in the 1950s when he was an assistant professor at Princeton University.
Then there was a 20-year gap, perhaps?
More like a 30-year gap between the two inventions.
Amazing. Then what happened when Bohm refloated the idea? Was it accepted, rejected, attacked, a little bit of both?
Well, a little bit of both. David Bohm was an interesting person. This was during the McCarthy period of all the rabid anti-communism in the United States. And David Bohm, like his supervisor, J. Robert Oppenheimer, and many of the people who were around Oppenheimer, had flirted with communism in the 1920s and 1930s. And as a result, just around the time he came up with this new version of quantum mechanics, he was called before the House Committee on Un-American Activities, and he refused to testify, and he was cited and charged with contempt of Congress, which he was eventually acquitted of. But meanwhile, Princeton did not renew his contract, and he, as a result, couldn't get a job to continue as a physicist in the United States and had to move to Brazil, where they were happy to welcome him.
Interesting. And so did his rediscovery of de Broglie's work then lead to a new generation of realists?
It did eventually, but the reaction at the time was to acknowledge that the theory existed and did what he and de Broglie said it did, but to ignore it. In fact, there's a great quote. There are many good quotes of why people talk themselves into thinking that the best thing to do is just to ignore it as irrelevant. But indeed, J. Robert Oppenheimer, who had been his mentor and thesis advisor and was then director of the Institute for Advanced Study, very famously said, if we can't disprove David Bohm wrong, we must all agree to ignore his theory.
That's not very scientific.
Yes, one wonders. Of course, Oppenheimer was a very good scientist, but he also had problems of his own with the government at about that time. And he had good reason to perhaps want to distance himself from David Bohm, who could be more easily painted as a communist or communist sympathizer. The story is very complicated, and I started to look into it, but it wasn't my main intention. I wanted to tell stories about science to help people understand the scientific issues, but I did not style myself as a biographer. I think there is great history of science and history in general waiting to be written here. Just one aspect of it, let me leave as a hint, is that David Bohm and Einstein were very friendly, and most of that is unrecorded, but they seem to have had some mutual friends in the area and to have communicated through these mutual friends. And it was Einstein. You see, let me go back a step. Why did David Bohm come to reinvent this pilot wave theory, which gave a realist perspective on quantum mechanics? Well, it wasn't his area. He was a plasma physicist, but he decided to write a textbook on quantum mechanics because teaching quantum mechanics was one of his duties at Princeton, and he was dissatisfied with the textbooks that existed. So he wrote a brilliant textbook, which is still used sometimes to this day, which gave a strict defense of the Copenhagen point of view. And Einstein, the legend goes, called him in, saw his textbook, and called him in for a discussion. They were apparently already somewhat friendly. And Einstein somehow gave him enough of a talking to that it made David Bohm go back and reconsider what he had written in defense of the Copenhagen view. And that led directly to his playing around with the equations and the principles and reinventing the pilot wave theory, all within a few weeks of his conversation with Einstein. By the way, just something else a good historian could look into. Freeman Dyson told me that when David Bohm first came to Princeton, he and Freeman had dinner together every night in the black side of town, which was forbidden, explicitly forbidden, but by the rules of Robert Oppenheimer for the fellows at the Institute to go slumming, as it were, to the black side of Princeton. But because of that, he and Freeman went almost every night together.
It's a bunch of interesting personal stories, as there always is. So why don't we start to move on to what happened after Bohm and the development of some of the scientific theories in the realist branch?
Well, so the key issue is, if you're a realist, what is the mystery about? If it's not about uncertainty, because the pilot wave theory explains what's going to happen, resolve the problem about uncertainty. If it's not about complementarity, what is the real mystery about? And Einstein, again, in his last paper about quantum mechanics in 1935, kind of almost accidentally finds the key thing. The key thing is what we call now entanglement. Entanglement says that if two quantum particles interact and then separate, and they may go a long way from each other, meters or light years, then they share properties in ways that can't be attributed separately to either one of them having a property. And this is entirely unlike the rest of science, the rest of physics. The idea that two particles distantly separated but having once interacted share properties which cannot be attributed to either one separately, or any combination of properties that either one separately may have. And this concept of entanglement, we understand now, is what makes quantum mechanics radically different from the rest of physics. Indeed, all the exciting stuff going on now, such as the attempts to build quantum computers, which would be able to break codes and do things that no normal computer could do in a finite amount of time, all rely on this property of entanglement. And entanglement is now something that the experimentalists study and control, indeed think of as almost as an engineering resource. So this property of entanglement should sound strange to somebody, because it means that there's a way in which the two particles are linked, even if they're very far apart from each other. And that violates the principle that physicists have held to be sacred, which is locality, which is that influences and forces travel through space from one point to another and don't act directly jumping over big regions of space.
Wasn't Einstein skeptical of entanglement? I think I recalled he had a paper. Was it the EPR paper?
This is the paper I'm referring to in 1935.
Yeah, where he called it spooky action at a distance and was really put the paper out to say there must be something wrong with quantum mechanics if this is what it implies. And yet, as I understand it, and you could correct me on this if I'm off, that modern experimental physics has shown that the EPR effect is actually what happens.
Yes. Now, what happened is that Einstein and his young collaborators, Podolsky and Rosen, Boris Podolsky and Nathan Rosen, fashioned an argument which assumed that there were only local influences and came to a conclusion that quantum mechanics had to be incomplete, to give an incomplete description of reality. And their assumption that there were only local influences was wrong, so their conclusion could not be held. But nonetheless, the paper was a breakthrough paper, because it led to the recognition of this property of entanglement, which was then found and measured by experimentalists to be real. Now, the next person in the story is an Irish physicist called John Bell, who was a particle physicist, and he came along in the 1960s, and he fashioned an elementary, very easy to formulate and check and prove theorem that if locality were true in cases like this where two particles interacted and then separated, then there was a certain constraint on measured values of certain correlations, and there's no reason to explain it here to your viewers. He could derive a certain constraint on measured values in some experiment. And the assumption was that when the particles were very far apart, that what one chooses to measure of one of them doesn't affect what's true about the other one. And if you're a realist and you believe in locality, how could it be that whether I choose to measure the position or the momentum or something else of a particle that's come over here to my laboratory shouldn't affect, it's obvious that that shouldn't affect what's true about a particle that maybe now is somewhere around Mars or Jupiter. And just making this assumption, which we call now Bell locality, Bell proved this inequality had to be true about the measured values of certain observables. And then he could do the calculation in quantum mechanics and show that the values predicted by quantum mechanics contradicted the inequality. So that meant that that property was false in quantum mechanics. But the dramatic thing, which was demonstrated a decade later, starting in the 1970s, is that people could do the experiment and find that the inequality was violated in the experiment. So without any reference to quantum mechanics, we have tested this assumption about locality, and it's false, and not just by a little bit, it's dramatically false.
I think this is big. This is a big story for our listeners, is that realism can include non-locality.
No, Jim, let me put it to you stronger. Realism or non-realism, non-locality is part of nature. This experiment doesn't assume any philosophy of nature. It just describes certain correlations between measurements you might make on a pair of particles and makes that one assumption. And believe me, people have combed this thing. It's a very short paper. There's not much to it. The other assumptions that go into the calculation are trivial things like probabilities or numbers between 0 and 1, which you can try to disbelieve if you want to get out of it. But I think everybody would agree that if probability means anything, the probability of something to happen is between 0 and 1. So people have looked for loopholes, people have looked for mistakes, and it's pretty remarkably solid at this point.
Those of us who looked into this as educated laymen have seen the claims that despite the fact that there appears to be an instantaneous effect faster than the speed of light between entangled particles that are far apart, there is no way to actually send information faster than the speed of light. Is that something you can talk about?
Yes. This goes back to the randomness you asked me about at the beginning of the show. Because if we look at any one detector for one particle, the outcomes are random. It's only when you look at the correlations of the statistics that you get by averaging over many instances of measurements on these pairs of particles that you see the observable and constructed that John Bell was pointing to and see that it violates the assumption of locality. So because quantum mechanics and quantum physics, as far as we can tell, is statistical, you can send information faster than light. Now, there are twists to this because let's go back to the pilot wave theory. In the pilot wave theory, how does it agree with the statistics of quantum mechanics? You have to make an assumption, which is that if you make an ensemble of trials, if you do an experiment over and over again, the wave is always the same wave, but you start the particle at different places and different runs. And what do you assume about how you choose the starting points for the particles in the different runs? You assume that the particles are distributed in the different runs by a probability that's related to the square of the wave. And that's called Born's rule. That was one of the fundamental principles of quantum mechanics, and it has to apply to the pilot wave theory as well. Well, there are 2 points of view to take to this, the traditional one, and one which is argued for by a contemporary physicist called Anthony Valentini. Most people, including Bohm, and for that matter, de Broglie, to the extent he understood this question, would have said that's one of the assumptions, it's one of the inputs of the theory, that you just have to distribute the particles according to that probability distribution related to the wave. What you can show is that once you've done that, initially it stays that way, so that as the wave evolves in time and changes, and the particles move around guided by the waves, the probability distribution always stays related to the square of the wave. And that's an important result that tells you that the results of any experiment are going to agree in pilot wave theory and in ordinary quantum mechanics. But Anthony Valentini said, supposing that you start off with a probability distribution different than that related to the square of the wave, you just put the particles in any old way you want, different from that assumption, what happens then? And he called that being out of equilibrium or out of quantum equilibrium. And Anthony Valentini was able to prove 2 remarkable results about that. One of them is that the system will evolve in time so that pretty quickly it gets back to the Born rule. So that even if you start off with a probability distribution for the initial particles different than the square of the wave, everything somehow conspires so that pretty soon the distribution is the same one, like the square of the wave. That's the first remarkable result. The second one is that during the period, however, when you haven't reached the square of the wave as the probability distribution, you can send information faster than light.
Have there been a demonstration of that?
People have tried, not that hard, but people have looked for that and so far not found it. It's given rise to any number of science fiction books, some of them good, some of them, well, I'm not really standing in judgment of science fiction, but science fiction books and ideas of varying quality in which people, aliens or the military or little high school kids or not so little high school kids, use this to send information faster than light. But it's standing as an open hypothesis.
And is there a well-defined set of experimental protocols that could demonstrate this if we had the right apparatus?
Yes.
That's very interesting. I'll have to keep my eye on that. Another realist branch of the tree is Everett and the multiverse. Could you tell us about that?
So one of the things about the Copenhagen interpretation is that it assumes that the world is divided into 2 parts. The quantum system, which is what we're trying to model using quantum mechanical ideas and mathematics, and the outside rest of the world, where the observers and the measuring instruments and the clocks and the rest of us live, which is assumed to be described by ordinary, that is, pre-quantum or Newtonian physics. And so Bohr and the Copenhagen people require us to always treat a quantum system as a small part of the universe and treat the rest of the universe as if quantum mechanics didn't apply to it, but Newtonian physics still apply. That is, in our part of the universe, the Newtonian part, There's no uncertainty. Everything always has a definite value independent of how you measure it and so forth. Well, one of the questions that became interesting during the 20th century as all this proceeded is cosmology. Because meanwhile, Einstein invented general relativity, and people began to apply it to models of the whole universe, to study things like the expanding universe as discovered by Hubble. And that's become quite a big and successful subject, modern cosmology. So what does that have to do with quantum mechanics? Well, if quantum mechanics can only apply to a part of the universe, you have a bridge, a gap there that's hard to bridge. And so Johnny Wheeler, who is one of the great visionaries of 20th century physics, used to ask himself and his students, could you devise a version of quantum mechanics that you could apply to the universe as a whole, where you wouldn't have to make this separation into the quantum world and the classical world? You'd somehow have to acknowledge, frankly, that the observer is part of the world and the world is one, which is a quantum world. So could you make a quantum mechanics which was a description of the universe as a whole? And this was a huge challenge. And my personal belief is that no, to make a theory of the whole universe, we have to go beyond quantum mechanics. That's part of the search for completion of quantum mechanics. But one of John Wheeler's students was Hugh Everett in the 1950s, came to a proposal about this. And the proposal was to remove from the formulation of quantum mechanics everything about measurement and probabilities and just leave an equation by which the wave propagates. The wave is taking the wave side of the wave-particle duality. There's a wave equation called the Schrödinger equation. And then there are other equations that describe measurement and probabilities for measurement. And Everett said, supposing we just take the theory to be given by the dynamics of the wave and we throw away the rest, can we make sense of that truncated version of the theory? And because there's no explicit mention of experimenter and observer, could we maybe apply this to the universe as a whole? Now, there are two problems with this. In fact, there are huge problems with it. But one of them is, what is he supposed to do with the fact that when you make a measurement, sometimes there's one outcome, sometimes there's another outcome. Sometimes if you have a particle in a ground state of an atom, an electron in the ground state of an atom, you ask, where is that electron? Sometimes it's on one side of the nuclei, sometimes it's on the other side of the nuclei, sometimes it's close, sometimes it's far. But there's always a definite outcome to your asking the question, where is the electron? So how does this theory of the wave, which doesn't mention anything about measurement or probability, deal with that? And Everett's proposal was radical and shocking. He said every time there would in the usual quantum mechanics be a choice like that, where there could be different outcomes, I'm going to postulate that the universe splits into different universes. And in each, there's a possible universe which actually exists for each possible outcome of the quantum experiment, of every quantum experiment. So every time in nature, the cat could be alive or dead, or the particle could be decayed or not, or any of these probabilistic things. There's a different version of reality. Reality is continually splitting into different versions, or as he called them, branches. And we as observers are splitting too, so that there are enormously large multiple number of copies of each of us and all of us in all of these different universes. It's completely insane.
For the listeners, I'm assuming that we're talking about a truly gargantuan number of universes, like every radioactive particle, when it splits or doesn't split in any instant of time, is presumably yet another fork in the multiverse.
Now, the story of this is that it became controversial. A lot of thinking was done about it. Hugh Everett himself left physics and went into defense work, being a physicist and engineer for defense contractors, and had apparently quite a successful career in that domain, and kept up with the debates, but never went back into science. But many people have thought about it. There are several questions which you have to address right away. One of them is, how do you account for the probabilities that we see in ordinary quantum mechanics? When we make experiments, we see the theory predicts that half the time the particle is decayed by now, and the other half the time it's not, and that varies as time goes on and more particles are decayed. So there's a lot that quantum mechanics predicts about probabilities. Where do they come from if the Everett proposal is true? Because in the Everett proposal, every one of these outcomes exists not with some probability, but with probability 1. Each exists with probability 1. And the only question is, what do you experience on the branch that this particular version of you that I'm talking to?
Doesn't seem to be a contradiction to me. I mean, if you go down the branches and you just happen to go on the branches of white, black, white, black, black, white, white, that's what you happen to see. And because all of our experiments don't happen simultaneously, I don't see a contradiction there.
There's not necessarily a contradiction, but you still have to ask the theory where the particular probabilities that quantum mechanics predicts come from.
The nature of the branching then, essentially.
Yes. One way to say it is that you have to reproduce this rule that I was telling you about a few minutes ago. The probabilities are proportional to the square of the wave, which is called Born's rule. There are sort of two stages in the history of this. One of them is Everett, who wrote this in 1957, and a number of people since who attempted to make use of it. And this kind of, this has not been an area where I work directly, but I certainly know many of these people and admire many of them, even if I find the idea very unsettling and unconvincing. There's a kind of first stage where people finally realized that Everett didn't have all the answers and that the Everett theory, as described in his papers, is not adequate to address all the questions it must. And then there's a group of mainly philosophers, although they're led by one brilliant iconoclast, the physicist David Deutsch, who's somebody that I admire enormously, even as I disagree with him about so many things. I think he's a great scientist. And his books are very worth reading, very provocative. So David Deutsch and then a number of philosophers at Oxford University made a much more sophisticated version in which they connected these questions about probabilities in the Everett world to questions about how you make decisions given probabilistic knowledge of your circumstance, a branch of probability theory that has been developed and is applied in the investment world or in a number of other practical circumstances called decision theory. So it was David's brilliant idea to apply decision theory to this question. That is, if you were an observer in an Everett world, there are no probabilities, but you still have to make bets. And what wisdom guides the bet you make when you bet which branch you're going to be on, where the particle went left or the particle went right. And so this is a new part of the subject, and there are lots of ins and outs of it. So here's what I regret for the reader. So I wrote these two stages in the development of the theory became two chapters in my book, the chapters 10 and 11. And I think I misjudged. And if somebody has tried to read them, I freely confess that I kind of misjudged how hard these things were. And probably we shouldn't have put them in a book meant for, as you put it, an intelligent but popular audience. But maybe the reader can decide. In any case, it's a fascinating subject. In the end, the answers are unknown. That is, the experts themselves are, as of this moment, highly divided as to whether real logical and mathematical sense can be made of how you pull out probabilities from this theory. And it's a fascinating story, and it's ongoing.
I'm going to throw out an interesting lunch conversation I had with Murray Gell-Mann once at the Santa Fe Institute. That was one of the joys of being a researcher there was you got to hang out with people like Murray and, just have random discussions. And I went down the quantum interpretations discussion with him one day and said, "Hey, Murray, what do you think?" And I realized he's written on this, but he gave me a shorthand answer, which I have not been able to find him ever putting in writing, which he called the as if many worlds interpretation. He said, "You know about Everett and his multiverse?" And I said, "Yeah." And he says, "Imagine Everett is right about the math, but by some magical mechanism, which we do not understand, only one of the worlds actually happens at each such branch. He says that was his best gut guess of the best interpretation out there.
That's interesting. I never heard him say that either. But Murray did write a number of papers on the interpretation of quantum mechanics, most of them with Jim Hartle, who was a good friend of his. And they espoused something that they called the consistent histories interpretation of quantum mechanics, which I suppose is something like what you just described. It's an Everett plus rule for when you can regard the world as real rather than just a fictional possibility.
He certainly seemed to be a realist. I mean, he would denounce people that, I remember him saying once, some people say if you don't look at the moon, it's not really there. That's ridiculous. The moon's always been there. So he would certainly seem to have been on the realist side of your realist, non-realist divide.
Jim Hartle was more adventurous in his anti-realism. He basically said realism, schmealism.
We've talked about other people's theories on the realist branch. Lee, what's your program? What's your best ideas about quantum foundations?
So, Jim, I see the problem of quantum foundations as part and parcel of the problem of quantum gravity, the problem of how to unify quantum physics with our understanding of space and time and gravity, which most of what we know about that is coming from Einstein's theory of general relativity. So one way to think about this is unifying quantum mechanics with general relativity. And to me, that's what I mean by Einstein's unfinished revolution. Einstein instigated relativity theory in 1905 with a special theory, and then in 1915, 10 years later, with a general theory, which included space and time and gravity. And at the same time, in 1905, he instigated the quantum revolution. And I think that both revolutions are still in progress and will culminate simultaneously. So for me, the biggest clue is what we were talking about a little bit earlier, non-locality. Quantum mechanics is describing a world somehow hidden behind our world in which space is not fundamental, in which whether two particles interact has something to do with their history, but not with whether they're near to each other or far to each other at the moment. In other words, entanglement. To me, entanglement is more fundamental than space. And so I have a program of research designed to find the completion, the theory which is the completion both of our understanding of space and time and gravity and our theory of quantum phenomenon. And I'm a realist, very, very much so. So I don't make any compromises with complementarity or Copenhagen. Now, I believe three other things to put everything on the table. One of them is that between space and time, time is really real. Time is fundamental. Time is irreversible. The feelings we have, the experience we have of the passage of time from the past to the present into the future is not an illusion, is not somehow a statistical illusion or misleading, but it's really how nature is constructed. So I'm what is called sometimes a presentist. I believe that what's real and what's true in the world is the present moment, which is evolving from the past through to the future. I'm also a relationalist, which is that I follow the philosophy of Einstein and Mach, and going back to a great philosopher called Leibniz, that the quantities that physics is interested in, like motion and position and state, are all about relationships. They're about relationships of the particle or the system we're studying with the rest of the universe. There are no absolute properties. There's no absolute meaning to where something is or how it's moving. All of these are aspects of relationships. So I try to construct a theory that is realist, that is presentist, that is relationalist, and that can give us back in the appropriate approximation quantum theory and general relativity. So that's kind of a tall order, but that's the world that I play in, the goals that I work for.
I think that's interesting because it gives you a parallax, so to speak, on the problem. People working just in the quantum world are looking at nuances there. You're looking at it from both within the quantum world, but you're also looking at it from the relativistic large scale at the same time. This may give you a unique way of thinking about the problem.
Yes, I think it gives me a lot of ingredients and direction. I agree with that. I should also say that I have wonderful company. At different stages of this work, I've been definitely blessed to have good collaborators and people who are incredibly insightful and smart and provocative in their thinking. So I want to mention them: Roberto Mangiabera-Unger, Fotini Marcopulo, Marina Cortez, Stefan Alexander, and a bunch of others, because without them, I would really be nowhere. About half my work in this area is single-authored papers assigned by myself, but very much under the influence of these and other people, and of course, all the great thinkers as well. Now, really, ever since my career started, during my first postdoc, I've every 5 or 6 years published a paper which was a proposal to make this relational completion of quantum mechanics. And there have been a number of different versions of it. They all concur that that entanglement is primary, that non-locality is primary, and indeed that causation and evolution in time are primary things, but the primary description doesn't include anything happening in space. That things developing in space are a kind of illusion, like temperature and pressure in thermodynamics. They're consequences of looking at things on a large and very average and coarse-grained sense, and that if you look specifically at what is really happening, there's no space. There's just events and causes of events.
And now, as I recall from your previous book, Time Reborn, I was really taken with that book some time back. And as I recall, one of the predictions you made, or I don't know if prediction is the right word, maybe it's a prediction, a implication of your thinking was that this relationalist geometry of what we call space, but you have a different metaphor. If your theories are correct, we should find non-local connections. If we think of space as a very, very fine grid with neighbors, kind of like a screen in your window. If I read it right, if I interpreted it correctly, you were saying there was like a thread that would come up off the screen, go 3/4 of the way over the screen, and come down on a new intersection and provide a shortcut across space.
Yes, this was an idea we developed with Fotini Marcopulo, and she called it the disordering of locality.
Yeah, and I thought that was just wow. And it also struck me that maybe there was an experimental way to see if that was true.
Well, maybe. And we spent some time on and off thinking about that. There was one paper that I wrote with a student in which we used these non-local connections as part of the dark energy. The dark energy being this mystery in cosmology of a substance that seems to fill the universe and behave like an energy that's distributed throughout the universe, a kind of energy of empty space. And there are other consequences that we've thought about from time to time. The version of these ideas that I'm engaged in now, so as I said, mostly I've been working on quantum gravity and occasionally other questions, but every 5 or so years, I went back and thought about these problems in quantum foundations and got a little further. I knew a little more and had a little different toolkit and developed a different proposal or a different version of this theory that I described. The present version is called the causal theory of views, and it's a kind of culmination of 3 different ideas developed with different people. One of them is a theory of the universe is based on causal evolution, and we call it the energetic causal set models that we developed with Marina Cortez. Another is an idea called relative locality, in which there's a kind of relativity principle that applies to whether something is local or not that we developed with with several friends and colleagues, Laurent Friedel, Giovanni Emiliano Camellia, and Yura Kowalski-Glickman, and other people who contributed to. And the last is an approach to what is quantum mechanics, to reinventing quantum physics based on some very different assumptions that I call the real ensemble formulation that I've been developing for about 6 or 7 years. And the three of these things I'm just telling you the names of things, put together result in a theory called the causal theory of views that I've published one paper about, and I'm quite struck with and am wrestling with now. But I've managed to show that there are some approximations to this theory that can be constructed, one of which gives back ordinary quantum mechanics. And I'm working on more sophisticated things that have to be true.
Very, very interesting. I got so many other topics here on my questions list, but let's jump to one a little further afield, and one that regular listeners of the podcast will be familiar with. I'd love to hear your thoughts on the Fermi paradox. And for the new listener, the Fermi paradox references a discussion that happened at the lunch tables back at Los Alamos during World War II, and they were working on the atomic bomb, and a bunch of young, smart guys were sitting around debating how many intelligent civilizations must there be in the universe. And they would take some assumptions about how often life evolved, how often life became intelligent, etc. And they sort of roughly came to a conclusion that there had to be hundreds of thousands of intelligent species in the universe. And then Enrico Fermi, one of the most distinguished physicists at Los Alamos, came over to the lunch table and said, "Okay, but where are they?" And since then, this question, this Fermi paradox, has been something that a number of people have been thinking about. And it's a really important and deep question. And sort of at the broadest level, there's two forks. We've been looking now for 60 or 70 years for signs of other intelligent life in the universe, listening on radio telescopes, looking for possible artifacts, looking for life of a different sort than our own life in the ocean. That's a recent attempt. And so far, it all comes back zero. Everything we can see in the universe appears to us, at least, to be dead. And there's two basic forks on that fact. One is that there are none, that we are, for whatever reason, the only advanced technological intelligence society, at least in our galaxy. But then there's the second branch, which says, no, they're out there, but for various reasons, we can't see them. Either they don't want us to see them, or their technology and their world has evolved in a direction such that they don't give off the kind of signs and artifacts that we might see. Lee, do you have some thoughts on the Fermi paradox?
I have really just one thought, which I put in my first book, Life of the Cosmos, which is that we should introduce a time scale and presume that there is a civilization out there, and they do explore. They are able to travel at not the speed of light, but maybe a thousandth or a hundredth the speed of light. And they do come by from time to time and look and see if intelligent life has sprouted and where intelligent life is likely to sprout. And the first question I asked is, what's the time period under which we can expect them to check back? And I thought a few 100 million years. And that's also because that's how long it would take life to evolve from say a stage of just prokaryotes in the ocean, in primitive ocean, to more sophisticated eukaryotes and multicellular creatures. And you'd only have to check back every few 100 million years to get an idea of what was brewing, so to speak. And also how long it would take to cross the galaxy at a fraction of the speed of light. Figured into that. So anyway, I said, so something between 10 and 100, a few 100 million years. Then the second question I asked, depending from that, is let's put ourselves in their situation. They're here on a primitive Earth. They see maybe some life in the ocean, maybe some plants, maybe even some very primitive land animals. And they are going to come back every few 100 million years. But just in case some intelligent life develops quickly, unexpectedly before that time, or maybe intelligent life visits from somewhere else, which is also possible, where they would like to leave a message. Where would they leave a message that could last 100 million years, so that if any intelligent life evolved or came by, they could leave a record of how to get in touch? And I thought about that and discussed it with a few friends. And the conclusion I came to is that there's only one reliable place they could leave it, and that's in the junk DNA of whatever species they find, in the mitochondrial DNA, because that doesn't undergo sexual division and selection. So I suggested, and I don't know if anybody ever took this up, going through the junk DNA or the mitochondrial DNA of a number of species, looking for artificial messages or patterns of signals, patterns of the genetic code that would be, through its formal structure, unlikely to have been generated naturally by natural selection.
Wouldn't that signal have been scrambled by now by mutations?
Maybe, but there's a mutation rate. And that's why mitochondrial DNA, the mutation rate, is all that matters. In the regular DNA, of course, it's scrambled every generation sexually.
Yeah, and also by things like crossover, which are, above and beyond the normal sexual reproduction. I would agree mitochondria would be the right place, but I have to look and see what the base rate mutation is on base pairs in mitochondrial DNA. And then, of course, many of those are likely to be fatal because the mitochondria DNA is small and it's very key to our metabolism. But anyway, that's an interesting idea for any biochemists out there to pick up Lee's idea and run with it.
Afraid I haven't gone back and thought about it much since that book, which was 1997.
Now, let me ask you about another one of your ideas from the past. The idea that our universe is a child of a previous universe, which is a child of a previous universe. Universes bloomed essentially out of the backside of black holes in their previous universe with a small jiggling of the laws of physics. And that there's this then tree of universes, and those universes which have lots of black holes have lots of children. And so universes have evolved. And as I recall in that book, you actually suggested there was some counterfactuals that might well soon be discovered in terms, was it curvature of the universe? I don't remember. But anyway, if you could update us on the status of that theory and whether there's been any new information that would rule that one in or out.
So that theory I called cosmological natural selection, and it was the subject of my first book, Life of the Cosmos. There isn't much new, unfortunately, I'm sorry to say. But the important statement is that I made, based on that theory in 1992, two predictions. One of them is that the heaviest possible neutron star would be no heavier than twice the mass of the sun, the so-called upper mass limit for neutron stars. And the other has to do with the hypothesis of inflation, that there's a huge expansion very early in the universe that gives the universe its ultimate size and shape and so forth. And the prediction from my theory for inflation is that only the simplest possible model of inflation, so-called single field, single parameter inflation, could be correct. And if there was a measurement of the details of the fluctuations in the microwave background or in the distribution of galaxies or in the other ways that we can measure the early state of the universe, they would have to be explained by that kind of inflation theory with one field and one parameter. And so far, both of those predictions hold up, although I should say that there are a few observations of neutron stars that come in with a higher mass as the central value. They have large error bars. And in all the cases in which neutron star masses are well measured, they're at most 1.97 times the mass of the sun. So they come very close to violating the bound, but don't yet violate it.
Okay, that's interesting. So the theory is still alive, hasn't been clearly falsified, but then there's no new evidence to support it either. Is that a fair way to describe it?
Yes. And the way that I saw this theory is not, I didn't make a big bet personally that the theory would be correct, that the assumptions that cosmological natural selection makes that you summarized would be correct, but it demonstrated something which I think is very important, which is that a theory, a framework in which laws can evolve over time, and remember, I believe that time is real and fundamental, has greater empirical success in the sense of makes more falsifiable predictions than a theory that assumes that the laws are eternal and fixed.
And it's also somehow, I don't know what, I would call it encouraging, that the future is not Laplacian.
Yes, I feel that way about it.
I can't put my finger on it scientifically, but just as a human being, I feel better about living in that kind of universe. Doesn't mean that's the kind of universe we live in, but I hope we are. Since we're talking about results with respect to theory, going back to our quantum foundations, what is the state of knowledge that helps us think between different quantum approaches, both things that are known now, or probably more interestingly, experiments that could be run relatively soon, or data that is likely to be gathered from our explorations of the universe that might throw some light on which of these many views of quantum mechanics are more right than the others, or that you're right and none of them are right and we have to rethink the thing. What is the factual and experimental environment for thinking about these theories right now?
It's fabulous. It's a fabulous environment. Let me mention two kinds of experiments which, in different ways, are testing the foundations of quantum mechanics. There's a proposal by Roger Penrose and a number of other people that the wave, a part of the wave-particle duality, the so-called wave function, from time to time spontaneously collapses. Now, to give you some background for this, one of the assumptions of the second part of quantum mechanics I described that has to do with measurement is that if you have a wave function which is spread out over a large area and you try to observe the position of the particle, you will discover the particle is at some position. And from then on, the wave function collapses to begin growth again from a concentration at that point where the particle was found. And that collapse of the wave function, or the projection postulate, as it was called by von Neumann, is a separate postulate, but it's part of the postulates of quantum mechanics. Now, the orthodox interpretation of quantum mechanics tells us that this happens whenever we make a measurement. But then that makes it very observer-dependent and intention and knowledge-dependent. Roger Penrose said, maybe there's some real physical reason that tells the wave function to collapse. There's some criteria that maybe is expressed in an equation which brings about the collapse of the wave function. And he hypothesized that this had to do with when gravity would be measurable. That is, if you imagine you have something like the Schrodinger cat, where the cat is either alive or dead. If there became a separation between the live and the dead cat large enough to make a measurable difference in the gravitational field, then that would trigger this process of wave function collapse, according to Roger Penrose. And the sensitivity to do that experiment, in other words, to see a new quantum effect which is not part of the standard theory, coming from trying to locate a mass which is a big enough mass that it could affect the geometry of space and time through general relativity, is just about testable right now. And there are, in the last year, a number of papers by several different research groups, I think all in Europe, describing concrete plans to do such an experiment. And that's extremely exciting. The other thing that's extremely exciting to me is the growth in the size of the molecule that we can treat as entangled. See, I've described entanglement as these correlations or shared properties, but entanglement has an enemy, which is noise, random thermal noise coming from the fact that everything is randomly in motion because everything is at some temperature. And in order to see the effects of entanglement, you have to somehow kill the effects of the random noise that permeates everywhere. And people are learning to do this. And as they do it, the size of the quantum system, which can be studied with respect to entanglement and its related properties, gives up a little bit. And there are larger and larger systems of entangled quantum states that are being produced in the laboratory. And this is very exciting because it seems to me, in the kind of theories that I make, if there's a place that quantum mechanics breaks down, it's this regime when we start to describe entangled states of a large number of particles joined together. Not just two, as in the Einstein-Podolsky-Rosen argument, but 10 or 20.
Yeah, I presume the escalating work in quantum computing will be focusing on some of these from an engineering perspective, if not from a scientific one, and might well develop some technologies to be able to see more deeply into questions of this sort. Well, I'd like to thank you, Lee. I know you have to go. This has been an amazingly wonderful conversation, everything I was hoping it would be and more. And I would encourage our listeners to go out and look under Lee Smolin in Amazon and take a look at some of his books. They're all interesting. And this has been great.
Thank you, Jim. Thank you very much for the opportunity.
Production services and audio editing by Stanton Media Lab. Music by Tom Muller at modernspacemusic.com.